Today, we're diving into the microbiome world to tell the story of a bacterial family that's, well, mostly harmless, except for one really, really nasty cousin. This is the story of Corynebacterium.
So, let me kick this off with a question for you. What could the totally normal bacteria living on your skin possibly have in common with a disease so brutal it can actually stop your heart? The answer, believe it or not, is that they're related. And that crazy contrast is exactly what we're going to unpack.
All right, first things first, let's meet the family. The vast majority of Corynebacterium species are what scientists call commensals. Basically, they live on us and in us, and they don't cause any trouble at all.
And here they are. Many of these species are just a totally normal part of our body's ecosystem, our flora. You'll find them on our skin, in our noses and throats. They're pretty much everywhere, and most of the time, they are just quiet neighbors minding their own business.
But when you get them under a microscope, they have this really unique look. They're gram-positive bacilli, which tells us about their cell wall, but it's their shape that's the real giveaway. They're often described as being club-shaped. And see those dark spots inside? Those are called volutin granules. Think of them like little storage lockers where the bacteria keeps its phosphates.
And here's their most distinctive feature. The way they divide and stick together creates these sharp, angular clumps. Early scientists looked at this and thought, wow, that kind of looks like ancient cuneiform writing, or even Chinese characters. It's a pretty cool signature look.
So just to quickly run through the family traits, they're part of our normal flora. They have that distinct club shape and staining pattern. They can live with or without oxygen, and they don't form spores. All in all, a very common and pretty successful group of bacteria.
But like in any family, there's always one that breaks the rules. And this one is a real problem. It's time to meet the notorious pathogen, Corynebacterium diphtheriae. So what's the big difference? What separates the harmless, everyday Corynebacterium, which are sometimes called diphtheroids, from the one that causes the deadly disease diphtheria? It really all boils down to one single devastating weapon, a powerful exotoxin. The harmless ones don't have it, the dangerous one does. Simple as that.
And even within this dangerous species, there are levels to the threat. Scientists have sorted them into three main types. You've got gravis, and just like the name sounds, grave, it's the most severe. Then there's intermedius, which is, well, in the middle. And finally mitis, which is the mildest of the three, though still no joke.
Okay, so this brings us to the absolute heart of the matter, the toxin itself. This thing is an incredibly efficient and potent biological weapon. And to really understand diphtheria, you have to understand how this toxin works. The diphtheria toxin is what we call an AB toxin, and you can think of it like a sophisticated two-part missile. Fragment B is the guidance system. It's the key. Its whole job is to find the right target on one of our cells and unlock the door to get inside. Fragment A? That's the warhead. That's the weapon that does all the damage once it's been delivered.
So let's follow the attack, step by step. Here, in step 1, you can see fragment B, the key, locking onto a very specific receptor on the surface of one of our cells. It's a perfect fit. Once it's locked on, the cell is basically tricked into pulling the entire toxin right inside. So now the toxin is inside, but it's still contained in this little bubble, a vesicle. As the conditions inside that bubble get more acidic, a critical change happens. The bond holding fragment A and B together breaks, and fragment A, the warhead, is unleashed into the cell's cytoplasm. And right here, this is the final knockout punch. The free-floating fragment A is an enzyme with one and only one target, a molecule called elongation factor 2, or EF2. Now, EF2 is absolutely critical for the cell to build proteins. And proteins are, well, they're everything. The toxin finds EF2 and shuts it down. Completely.
The result is immediate and catastrophic. The cell's protein factory grinds to a halt. It can't build anything, it can't repair itself, it can't function. The cell simply dies.
So, what does this microscopic act of sabotage actually look like in a human being? This is the scary part, where a simple sore throat escalates into a body-wide systemic threat.
Let's just trace the path of this disease, right? It usually starts in the throat or nose. The bacteria start multiplying, just pumping out that toxin. The toxin kills the local cells, which forms this thick, gross membrane. But the toxin doesn't just stay there. It gets into the bloodstream and travels, causing terrible damage to the heart and nerves. And this is what it looks like.
These are the classic, terrifying signs of diphtheria. On one side, you see the massive swelling of the neck lymph nodes, creating what doctors call a bull neck. And on the other, that is the infamous pseudomembrane. It's a thick, gray, leathery sheet of dead cells and gunk that can literally cover the airway and choke a person to death.
I mean, death from diphtheria can come from so many different angles. It can be mechanical, suffocation, because that membrane physically blocks your breathing. Or it can be systemic, as the toxin spreads and causes myocarditis, a really dangerous inflammation of the heart, which can then lead to total circulatory collapse.
It is a truly terrifying disease, but thankfully, the story doesn't end there. The fight against diphtheria is actually one of science's great success stories. So, how do we fight back?
Well, first, you have to know what you're dealing with. Diagnosing it is a careful, methodical process. It starts with getting a sample, usually from a throat swab. Then, lab techs use special stains to look for those signature club-shaped bacteria. They grow it on special media to isolate it. But the final, most critical step is proving it. They have to confirm that the bacteria they found are actually producing that deadly toxin.
When it comes to taking action, we really have two different game plans. There's treatment for someone who is already sick. That's a race against the clock to neutralize the toxin that's already in their system and kill off the bacteria. But the absolute best strategy is prevention, building up immunity before you ever get sick in the first place.
And our #1 weapon for prevention is vaccination. The strategy is so clever. Instead of targeting the bacteria, the vaccine uses a harmless, deactivated version of the toxin called a toxoid. It only takes 5 recommended doses throughout childhood to build a powerful, long-lasting immunity that can stop the real toxin dead in its tracks.
So we end up right back where we started, a common microbe on our skin and a devastating killer, all separated by a single toxin. The story of diphtheria isn't just about a scary bacterium. It's a powerful reminder of how, when we understand a disease at its most fundamental level, we can learn to defeat it. This thing was once a top killer of children. So the question is, what does its defeat teach us as we face the diseases of tomorrow?